Recording is rolling. It is Wednesday, November 6th. So near the beginning of class, we're going to look at this car brakes to a stop scenario and say, what's the braking distance? Now, this is something that you could solve before using dynamics and kinematic motion. So we'll solve it that way. And then we're going to use the new method that you guys just learned in the last couple of days. And I'm going to show you guys that it is, in fact, the same distance. But also that this new method, you can actually solve it faster using this new method. So that'd be true too. All right. You guys remember yesterday, those 3-page tables. Where have I got it? Right here. Guys, have these out because I did a couple of these with you guys and then gave you guys the last about 20 minutes of class to do as many as you could. We're going to go over the solutions and see how you guys did. See if you can think in terms of this new method. That again, I know you guys only a couple of days, but how you guys are doing? All right. Oh, I really do need to get you guys up and moving around and working on some labs. So here, just to show you guys what's coming up pretty soon. I do have 3 labs lined up for this unit. One is I got these little poppers, right? So you guys see it looks like a little dome. You can hold it inside out, put it down on the surface. Let's see, watch this thing. See, what? Oh, that was a dud. Oh, fail. Oh, all right. And it could pop up to some height. Let's see, that's the same against the camera. That was an awesome camera shot, though. Let's see it one more time. Pow! Oh, up it goes. Huh. I wonder if you could calculate the energy associated with that. Hold on to that idea. We'll do that one of these days upcoming. All right, pendulum maximum speed. Do I have I know I got a poster for this one too, coming up pretty soon. All right, guys, as a pendulum is swinging, guys, which point do you think it's moving the fastest? Which point? The very bottom, right? And you can think about that in terms of conservation of energy. Guys, what kind of energy all the way at the top? Potential. What kind of energy right at the bottom? You guys remember Paul Hewitt yesterday with the bowling ball? He didn't get his teeth smashed in? Yeah, right. About conservation of energy. So I'll have you guys bring up some pendulums. You guys can use the speed gates to see empirically what is the speed at the bottom. You're going to compare that to what if you use this conservation of energy method on paper? What should it be? And I remember last year when I did this, the numbers matched, and let's see if it does for you guys too. All right. Also, there's another lab coming up. All right. So on my desk, this entire semester, I've had a pulley system rigged up. You guys see this pulley system right here. So I'm gonna have you guys rig up some pulley systems. See what is the mechanical advantage. You can get you can increase your strength with a pulley system. You guys see here. I know this off screen if you're watching this video. Use your imagination. I'm holding right now a small weight. This is what 5 newtons right there. And then I see a big old weight, 10 newtons right there. Because if I let go, which one moves down? The light one or the heavy one? The light one moves down, the heavy one moves up. How is that? Because there's a mechanical advantage involved. Also, compare those distances that they move to. That's interesting. Different distances. Okay, so I'll show you guys how you can amplify your strength with a machine, a simple machine, and a pulley is a type of simple machine. All right, that's an upcoming lab, so look for that. All right, AP Unit 3 progress check has been open. All right. So be looking at those questions. They're all energy and work questions, right? There's probably some power questions. We haven't quite got to power. We're getting there. We're going one day at a time. All right, so it might be a good idea. Read those questions against the ones you can answer. Maybe we haven't covered 100% of the content yet, but we're getting there one day at a time. All right. Oh, some other things coming up. Guys, Monday, is there school Monday? No, because Veterans Day, right? Veterans Day is Monday, so there's no school. All right, also Tuesday, guys, Tuesday there's testing going on. I think it's called FCLE, is that right? Like that, probably a bunch of you guys are taking it. All right, so there will be testing in this room, which means you guys are not going to show up to this classroom. So my first 4 classes, that's true. All right, so got some relocation data here. Let's see if I can dig up the Excel page that tells you where you're testing if you're testing, okay? All right, so you guys good with, all right, bunch of stuff coming up here. All right, you guys good so far with the agenda? All right, you guys ready to solve a car breaking to a stop? Car breaking to a stop. So like I said, we're going to solve this 2 different ways, and I'm going to make the claim we're going to get the same answer. No matter how we solve this. So let's get a car breaking to stop. Here, the first way we'll do this. I'm going to show you guys like the forest for the trees roadmap. As we're going to do this free body diagram, say what's the rate the car is slowing down. This is the old method. You could have done this like last week, right? What's the rate the car is slowing down? We'll call that acceleration. Then we're gonna, hey, you guys remember this acceleration bridge? We're coming from this side right here. The car slowed down, we solve for acceleration. That gets us point right on top of this bridge. We're gonna go over to kinematic motion, and I wonder if you can solve for say like X. What's the braking distance of the car? Right? Right. We're about to do that first, and then later on, do I have Oh, okay. Later on here, after we do that, we'll do this method and see what we get for the distance. And I guarantee you it's going to be the same thing. All right, you guys ready for that? You guys ready? All right, so let's get a car. Show me a car. All right, you guys draw a road. You guys draw a road in your notes. You guys draw a little turtle car. All right, and yep, this pen's working. All right, I'll get this car. A mass M. It has some initial speed V naught. Okay. I bet there's a coefficient of friction between the tires and the road. I bet there's a gravity field of the planet, and there's going to be some braking distance. I'll call it D. Why not D? Okay. All right. Let's get some numbers on the board. Numbers on the board. Okay, and then whoops. Final velocities, of course, 0 meters per second because it's braking to a stop. Okay. You might want to write a title on your notes. Car brakes to a stop. Okay, we're going to solve this 2 different ways. All right, I'm going to need some numbers. I need a mass of the car. I need a, say, a gravity field of the planet. I need an initial speed of the car. I need a coefficient of friction between the tires and the road. It could be static friction if this car has anti-lock braking system, right? If we're playing off that one. All right, so you guys catch up to that right there. Okay. All right. I'm gonna have you guys volunteer some data here. Let's go with Alec. Alec, give me a reasonable mass of a car. Yeah, let's go 200 kilograms. All right, got a little maybe one of those little smart cars. All right, might be like that. All right, Alex, give me your favorite gravity field. 9.8 meters per second squared. Boom, done. All right, how about Hans? Give me a starting speed of the car. 20 meters per second. Boom, in the book. Let's go. Mariah, give me a reasonable coefficient of friction. Huh? 0.68. All right, there you go. All right, boom. Yeah, all those numbers look reasonable. Good call. All right, we're gonna see what is the braking distance of this car. All right, you guys ready to solve this? All right, so let's do free body diagram on this car. You guys put a big old center mass dot on that car. All right, you guys do that? All right, guys, what's one force on this car? Yeah, gravitational force, it's weight. All right, so I'll label that mg, but you know what? Let's go ahead and tag a hard number to that. Guys, how much does that car weigh? Yeah, almost 2,000 newtons, right? And let's play off this more precise value of gravity here. So let's go 200 times 9.8, because 200 times 9.8 looks like 1,960 newtons is the weight of that car. All right, you guys got that? All right, 1960. Then, guys, what's holding the car up? Normal force, F sub n. And what's that equal to? 1960 newtons. That's right. All right. How about, now if the car's braking to a stop, what are the forces acting on the car? Yeah, friction between the road and the tires. Right. Oh, and you guys, of course, drew that opposite of the motion, right? I'll call it F sub FR. Right. Now, guys, there's a formula for friction force, either for kinetic friction or if you're maxing out with static friction. Right. How does it go? It's what times what? Exactly. Yeah. Coefficient of friction times the normal force. Boom, boom. Right. Coefficient of friction times normal force. And hey, we have numbers for each of those. You got a coefficient of friction of 0.68, and I got a normal force of 1960 newtons. Right. Can you guys calculate? Here, you guys do it. I'll calculate it off screen. Let's see if we get the same number. I got the coefficient of friction. I got the normal force. All right. I have a number on my calculator screen. What are you guys getting? Aha! Yeah, 1332.8. I'm gonna let's keep that extra digit. Why not? Right now it's crazy precise. So let's go 1332.8. That could be newtons. Boom. Right. So okay, so I got my forces. Right there. There's my weight. There's the normal force. There's the friction force right there. Boom, boom, boom. Right, you guys got three forces. Three forces. It's got. All right. Guys, what is the net force on the car? Yeah, the friction force. So 1332.8 newtons. right? Guess that. Right. Now, if you know the net force, what's the next thing I should be solving for? The acceleration. Yeah. Right. Of course, it's going to be a negative value because the car's slowing down. Right. Right. And how am I going to get that here? Oh, right here. Accelerate. Oh, did I pick the wrong pen? Throw that one out or something. Right. Acceleration equals, guys, what's the formula that I can use to find acceleration? F equals ma, right? Rearrange it. I'll get the net force acting on the mass. And you guys just told me the net force is the friction force. Okay? So it's really like that, isn't it? Friction force on mass. Okay? And we have numbers for those. So let's plug in some numbers here. I got the net force friction force is 1332.8 newtons. Right? Now, guys, that's a vector value, right? That's a vector. So if forward is positive, then really I should tag a negative to that, right? Okay, so I'll call it negative. Okay. And then that's acting on a mass of, ooh, we got a 200 kilogram little smart car. Oh, yeah. All right. All right. Now we can see what rate is this car going to slow down. I'm gonna make a guess. I'm gonna guess it's between 6 and 7 meters per second squared. All right, let's see. Let's see if it is. All right, so take 1332.8 divided by 200. Did I say between 6 and 7, right? All right, let's see. So acceleration equals, let's see, it's 6.664 meters per second squared. All right. Huh?
Why is it a negative in front of the?
Okay, because since these are vector values, the direction matters. If I call forward positive, I'm going to say it's going to break some positive distance going forward. Forward is to the right. This friction force is actually in the negative direction, right? So I can draw the arrow backwards and just label the number on it. But mathematically, I'll treat it as a negative value. Yeah, you could do that too. Yeah, you could do that. You could call left positive and right negative and say it's going to break a negative. Yeah, you could do that. Yeah. All right. All right. So you guys know the rate the car slowed down? All right. Now, guys, how did I know this was going to be between 6 and 7? I'll tell you guys how I know. Because this gravity field's pretty close to 10, a little short of 10. The coefficient of friction is like 0.68. And I know this in the back of my mind. Guys, this is what we just did. We just did this process exactly. Except here is in terms of variables. You can solve for any car on any road. Right? And today I decided, let's plug in the numbers first. Okay? But I knew that was what it was going to be. All right. All right. All right. Oh, okay. So now we know the rate the car's slowing down. But remember, our goal is to figure out how far does the car brake. So what should I do next? Kinematic formula time. Actually, let me find that list of kinematic formulas. It's in this. All right, let me do stuff. It's gonna be worth digging out here because here we go. Right. Now here, guys. I'm really thinking you should have these memorized by now. Of course, on the AP exam, you're allowed to have access to a formula page that also has a version of these formulas, right? Which are the first three. They're going to be right here. They're written slightly differently than I do them, so be familiar with that, right? But really, having seen these so many times and used them so many times, and they're kind of nice to have them on the exam, right? I'm really recommending you know these, right? So, guys, notice I never mentioned anything about a stopwatch, and I'm not timing how much time it takes for the car to come to a stop, which might be a really strong hint that it's going to be which kinematic formula. The third one, right? The third one, because I see a stopwatch here and I see a stopwatch here. Time. All right. But look at this third one. I got the braking distance here. I got everything else I need everywhere else. You guys ready to use that one? Right. Or in terms of this bridge, right? We just solved this. We got this acceleration, right? And now we're going to kick over to this is the third kinematic formula in disguise. It's equal to A. Okay. So let's go. Third kinematic formula. Guys ready for third kinematic formula? That's going to go final velocity squared equals initial velocity squared plus 2AX, right? Like straight off the page. Looks like that, right? Okay. Guys, what is the final velocity of the car? 0. Yeah, 0 meters per second because it's braking to a stop. Square that, still 0. Okay. The initial speed of the car, let's do in terms of numbers, was 20 meters per second. Guys remember that? Okay. So 20 meters per second. I think it's about 45 miles an hour, I think, something like that. Okay. Squared, right, plus 2 times, right, no, remember, guys, this acceleration is negative. You guys remember I made that whole point negative? So negative 6.664 meters per second squared. Okay. And then this x could be a generic distance. I'll call it d for the braking distance, just to match my picture. So this d is this x, right? Okay. Right? You guys see where all this come from? Right. And the rest of this is algebra. You guys can solve this, right? So 20 squared is 400. Subtract that over. That's like negative 400 meters squared per second squared. If you keep track of units, what's this number? What's that times 2? I got negative 13.328, and the unit is meters per second squared, and then times d distance. Okay. Oh, now guys, in this class, don't forget the units. A lot of students focus on, I mean, you need the numbers. Numbers are important, but don't forget the units too. Do you guys see the seconds completely cancel? And one of the meters cancels, which is going to leave you with some number of meters, hey, which describes the distance. So it works out. Right? Also, I have negative divided by negative. It's going to give me a positive distance because the car's going forward. That makes sense too. Right? Let's start. What's 400 divided by the answer? Okay, guys, what did you guys get? Braking distance. Did anybody get like 30 meters? 30 meters? Right, I'm getting like 30 meters almost on the nose. Yeah, right. That's right. So just that divided by that. I'm getting distance equals, right. I want to make sure I didn't make a mistake, but I think that number looks reasonable, right? About 30 meters. 30.012 meters, if I'm being crazy precise about it. Right. 30 meters and 1.2 centimeters. You guys got about 30 meters? All right. All right, you guys ready to do the work energy method? Work energy method? All right, guys, I'm guaranteeing you we're going to get the same braking distance. You guys ready for this? Right, using a completely different thought process, a completely different framework. Okay. So let's go back. Car brakes to a stop. All right, now we're doing the I'll call it the work energy method. Now, yesterday, this is one of the ones I was going over with you guys. I was telling you guys to use an open system. I'll write that out. Open system. All right, so we're just focused on the car. AP likes to ask questions about what's a closed or an open system. So a closed system is all the forces are internalized. Right? An open system, there can be an external force. In this case, the friction force is a net external force. Right? I'm just focused on the car. Right? So same question though. Same picture setup. For initial velocity, brakes to stop, Vf equals 0 meters per second. All right. So here's the framework. The sum of energy initial minus the work done by friction equals sum of energy final. Okay. All right, guys, good? Okay. Now, guys, what kind of energy did the car initially have? Kinetic energy. And what's the formula for kinetic energy? All right. All right, you guys are on 1/2 mv squared. All right. Here's your checklist to draw from. All right, they're all real short formulas. These aren't too bad to memorize, right? You guys can note these. Right? Yeah, 1/2 mv squared. Boom. Exactly. 1/2 mv squared. Okay. Minus, guys, what's the formula for work? Force times distance. All right, straight off here. Right? In fact, what force are we talking about? Friction force. So friction force times braking distance, which I think we're solving for, right? Equals, and what mechanical energy does the car end up with? 0 joules. Because it's not moving, so it has no kinetic energy. It hasn't rolled up any hill. Guys, if it rolled up a hill, then some of the energy would have gone to potential energy, right? But that didn't happen, right? So the reason it slowed down is only because of friction. So there's no potential energy, no kinetic energy. It didn't smash any springs. There's no attenuator. No, that's a 0. Right? Here, guys, if you held a thermometer to the road, there's a little thermometer on the road, right? And you measure the temperature before the car brakes, and you measure the temperature after the car brakes. Is the temperature of the road going to go up a little bit? Yeah. Do you think you could quantify that thermal energy and probably be equal to the original 1/2 mv squared? Right? Let's put some numbers to this. Figure out. So I got the car had a mass. What was the mass of this car? 200 kilograms, right? 200 kilogram. 200 kilogram car. it was going at 20 meters per second. 20 meters per second. Square that minus friction force. Oh, we calculated friction force already. You guys remember we did that over here? It's 1332.8 newtons. That's right here. 1332.8. That's newtons. Times breaking. What's that?
You have to make it negative.
Oh. Yeah, right. Okay. Here, I'm think of it this way. I could say in general this could be plus, but maybe plus a negative value. So I took care of the negative already. Think of it that way. Okay. Also, you know what I never actually explicitly mentioned yesterday, which kind of goes hand in hand with this question, like what's positive, what's negative, is guys, some values in this class are vector values. The direction matters. Some are scalars. Take a guess. What do you think energy is? Do you think energy is a vector where it has direction that matters, or is energy a scalar? Energy is a scalar. Yeah, energy is a scalar. Right. So what that means, it has no direction associated with it. So sometimes you have to use your mind and say, well, what makes sense? Is the friction adding energy to the system, or is it taking out? Well, cars breaking to a stop. It must be taking out. Right. That's something like that. All right. So let's get some numbers. How much energy did the car have initially? 1/2 mv squared. Right. So it had initially 40,000 joules. I could call that like 40 kilojoules, right? 40,000, but it looks like 40,000 joules. Right. And if I slide this over, that's 1332.8 newtons times the braking distance. Right. It's like that. One algebra step. Just divide the force over. Right? That's it. So what's 40,000 joules divided by 1332.8 newtons? Okay. Braking distance is. All right, you guys ready for this? Okay. All right, so here, it's all right on this right here. The answer has to be 30.012 meters, right? Right? Like down to the millimeter. Let's see if it's the same answer down to the millimeter. Oh yeah. Oh yeah. 30.012. And the unit is meters. There you go. Look at that. It's the same answer. Right? Right, guys good? Also, right, if you compare the amount of paper that I used to solve it, right, with the old method, I had to go through dynamics to get the acceleration, and then I brought out a new piece of paper to solve the kinematic motion to get to the answer. So that's like 2 pieces of paper. Right? Versus this method, oh look, it all fits nicely on 1 page. Solved it a little bit faster that way. Yeah. Right. So sometimes you'll see that too. Right. Right. You guys good? Right. So if you get this question as a free response question, right, now you have some options about how you want to solve it. Right. All right. All right, you guys good there? Good there. You guys ready for energy table? All right, so let's flip over to energy table. So gotta get this out. Oh, all right here, energy table. All right, see how you guys did. All right, so of course we did these 2 yesterday. All right, so moving on. All right, scenario number 2. A cannon fires a cannonball at some angle from ground level. Ooh, now guys, does that look like a projectile? Notice I didn't tell you the angle. I'm leaving this a little bit generic, but if I did tell you the blast speed and the angle, do you think you could solve for like either how high does it go or how fast is it going using projectile motion, right? Right, got vertical components, got horizontal components. Yeah, you could do that. That's one way you could go about this. Oh, and then now we have a different way to think about it. Of course, same answer. Right. So point A, guys, point A is where the cannonball has already left the cannon. It's already in motion. So whatever the blast force from the cannon is not part of the system. Right. Now you needed that to get the cannonball in motion, but the cannonball is already in motion. So I'm focused on the cannonball. Cannonball. Right. Just while it's a projectile in flight. Hey guys, while it's a projectile in flight, is there a force acting on the cannonball? There is. What is that force? Yeah, gravitational force. It's weight. In fact, if you draw a free body diagram, wouldn't you just draw exactly one force vector straight down? It's weight. Right. Right. So if I want to internalize all the forces to make it a closed system, I also have to include the what? The Earth. Aha. Yeah. So this would be called the cannonball Earth system. Okay. because they're pulling on each other. Right now, I've internalized all the forces. Okay. Whenever there's a height change and you want to consider gravitational potential energy, yeah, you also have to include the Earth to make it a closed system. Okay. That's another hint. I've seen that question come up a few times in the past. Right. So, what kind of energy at point A, where it's basically at ground level, but it's moving really fast? Yeah, kinetic. So there's your 1/2 mv squared at point A. Okay. By the time it gets to point B, where is the energy gone? Yeah, potential mgh. And is it still in motion? Yeah, it's moving to the side, probably a little slower than before, but it still has also what kind of energy? Kinetic. So say plus 1/2 mv squared. Now this v has a subscript b. Right, so it's a different speed. Let's see if you guys are following. Guys, which speed is faster? The speed at point A or the speed at point B? Yeah, the speed at point A. Yeah. Right. And in terms of conservation of energy, you could say like some of the energy went into lifting it at higher height, so it's going to slow down. Kind of like if you're in a car and you're like going up you guys know that what is it, Vera Boulevard has that like diverging diamond goes over the interstate, right? Suppose your car's like rolling up. Just the fact that it's rolling kind of uphill, it's slowing down, right? Because some of the energy is going into lifting it up. Kind of good. All right, so let's solve for the speed at point B. All right, let's do that. So got sum of energy at point A equals the sum of energy at point B. Here, I'm just doing this on this paper because it's a little tiny square here. Okay, so I got 1/2 mv squared at point A equals mgh plus 1/2 mv squared at point B. Right. I have 1, 2, 3 terms. You guys see 3 different terms. Right? Now, as long as the variable is common to all 3 terms, then it's allowed to cancel out. Is there any variable that cancels out? Yeah, the mass. So if you had a big old heavy cannonball next to a little tiny baseball, you fired them at the same speed, suppose you got them going at the same speed, then they would have the exact same motion side by side. Right? I mean, that's consistent with the thing we've done so far, kinematic motion days. All right, so what next? Hey, can I get rid of this fraction? I see a fraction here. That's kind of like, Right. Can I multiply everything by 2? And remember, if you want to multiply by 2, you have to multiply all 3 terms by 2. This is just one way to do it. So I'll have VA squared equals 2GH at point B plus, I got a VB squared. Right? Does that make sense? Right, a little algebra step. Right. Then subtract this over. So VA squared minus 2GH at point B, right, is equal to VB squared. And then, guys, the last step is to do what? Square root. Right, so VB equals, again, okay, so it's a big old square root. And it's the speed at point A squared minus 2GH. Okay. So I got. All right. All right, guys, good there? Right. Now, okay, so great. We got the answer in terms of variables. We made numbers. Okay. Oh, what I want you guys to see is, because there's a really common mistake to make, like especially if you're just starting out on this or right. Notice what this is not, what it is and what it is not. Let me write a different expression down here. What if I say this? VB equals here. I'll put a little question mark. Is this true? Okay. Hey, look, I see a square root of a square. Square root of a square. Can I just say, oh, VA minus square root 2GH? Can I do that? Can I do that? No. Cannot do that. Now, what if this was not subtract? What if this was multiply? If this was multiply, could I take the square root of a square? Yeah, that'd be okay. Right. But guys, anytime you're adding or subtracting, these are 2 different terms underneath that radical. You cannot just square root 1 and subtract the other. You can't do that. Okay. Right. Which you know what? I want to make a connection. Okay, so you guys wrote that in that box. Okay, put that. I want to make a connection here to this pendulum maximum speed. I showed you guys this real briefly earlier today. Okay. So this is Paul Hewitt with his bowling ball, isn't it? It's going potential, kinetic, potential, kinetic, potential, kinetic, like that. Okay. Notice that the answer to this, the speed at the bottom, final speed at the bottom, is pretty much what we just did. I got a big old square root. I got 2G. Now, if you do some geometry, this height change ends up being here. Let's do this real fast. Do you guys see a triangle here? You guys see a triangle? Right. If this string length is L, then this is also L, right? Right. And this triangle, is this L cosine theta? So is the height change just equal to the full length minus L cosine theta? Which is what I put here. And if you like, you could factor an L out, right? Kind of optional. You do that. Okay. That's this right here. So basically, what I'm trying to show you guys is this is square root 2GH. Okay, it's square root 2GH a little bit in disguise, isn't it? One more thing. What if you don't release it from rest? What if releasing from rest is all the black ink? What if you give it a push? If you give it a push, that's the gray ink, which shows it better. You guys see 1/2 mv squared there? And look how it translates to the answer at the end. I skipped a few algebra steps, but it's the square root of v squared plus and then 2GH, right? Which is exactly what we just did for the cannonball. It's the same thing, isn't it? Same thing, right? And notice what it is not. It is not the pushing speed plus square root 2GH. That's the wrong answer. It's gonna be the square root of push speed squared and then the 2GH. Okay? A little bit different thing. All right. Where are we next? Kid slides down a hill, length L. There's friction. Maybe he's on a sled and there's like snow. He's going down the hill, something like that. Right. Step it opens. This is the only other open system besides the car braking to a stop on this packet. So I'm gonna have either the kid or the kid in the sled be one object. If you said like the kid is an object, that's good. Right. Guys, the fact that the Earth is pulling down, maybe I'll also include the Earth. Right. Now, if I only include that in my system, it's still an open system because, guys, what net external force is acting on the kid in the sled? Friction. Yeah, friction force, right? From the surface, right? So that's why I'm considering it an open system. Right? So at point A, what kind of energy at point A? Yeah, potential energy, MGH. Right. And then in this bubble right here, I'm going to do kind of what we did yesterday with the car, right? Which is I say minus friction force times L, because isn't L the full length the friction force acts over? Right, guys see that? Right? Because L is the full distance the friction force acts over. And that's equal to, I mean, if he's sliding down, he probably has some speed at the bottom. That would probably make sense, right? He might even be speeding up. Right? There's no reason he couldn't be speeding up. Right. Oh, so 1/2 mv squared. That's at point B. So you could do that, right? Right, you guys good? All right, I'm gonna blow that up bigger here. Sum of energy at point A equals sum of energy at point B. Top of the hill, bottom of the hill. Right. So start out with some MGH. Right. Whoops. Sorry, minus work equals energy final. Right. Right, so subtract off, and then the work done by friction is force of friction times the length. Right? And then he ends up with, he probably has some 1/2 mv squared at the bottom. Okay, something like that. Sure. Oh, we'll decide that here. But before I go on, because what if there was no friction? If there was no friction, you could get rid of this, right? And look what you have. MGH equals 1/2 mv squared. Isn't that exactly like the Galileo question? Galileo dropping the ball, right? Because the reason I'm making this point is if there was no friction, if this was like an air hockey table, right? Do you guys see that the speed of the ball is the same whether you drop it off a vertical tower or if it slides down an air hockey table with no friction? The speed is the same at the bottom. Now, that doesn't mean it takes the same time to get to the bottom. That's different. It would take more time to get to the bottom on an air hockey table. But by the time it gets down there, if it had no friction, it would be going the same speed as if you just dropped it vertical. Huh, that's interesting, right? You can see that right here. Okay, but let's go back to this one then. Right, so I need to maybe multiply everything by 2 might be nice. Let's do 2 MGH minus 2 friction force times L, right, equals MVB squared. Right, maybe divide everything by this M, right? Okay, so it'll be 2GH minus 2, friction force times L, all divided by M, because you guys got to divide M on each term. Okay, that's VB squared. Okay, and then finally take the square root. So the speed at the bottom is, it's a big old square root, 2GH. Okay. In fact, if there was no friction, that would just be the answer, right? Speed square root 2GH, which you've seen many times before. Right, but if there's friction, I have to subtract that off. Minus 2 times the friction force times the length and then divide by the mass. That could be the answer. Okay, that fine answer. Right. If you want to go to a step deeper, let's go a step deeper though. Right. If you have this, that's fine. Guys, this friction force. Do some stuff with that. Guys, friction force. What do you know about friction force is equal to coefficient of friction times what? Normal force, right? Oh, thank you. And guys, normal force on an incline was equal to mg times what? Cosine of the angle from the horizontal. All right, is that true? Right. So if I substitute this in for this friction force right here, I could actually get the mass to cancel. So if you got a kid in a sled and he's got his friend next to him and they're completely different masses, I bet they could still slide down side by side because the mass is about to cancel right here. So I got the speed at point B is got a big old square root, got 2gh, I got a minus 2, but instead of friction force, I'm going to write mu mg cosine theta. Okay, I still need an L in there, extend my square root over that expression. It's a little bit short. And then divide by m. You guys see this m and this m? Okay, go away. Right, the m's go away. Okay. So this answer is also correct. It's just a little bit more detailed. All right, guys good? All right. Ready for our next one. Next one. Block spring earth system. Oh, whoops, I gave it away. Oops. So block spring earth system. Okay. Yesterday I was showing you guys a poster that was almost exactly this, really. Actually, it is the same answer. Let's see if I dig it up real fast. You guys remember this poster from yesterday? It's the exact same answer. Right? Slightly different geometry. Comes out the same. So that's it. Energy at point A. When you squash this block against the spring, all the energy is now in the spring. Oh, the spring, right? We'll call it spring potential energy. Oh, I should mention this too. Guys, here's another detail. If AP ever just uses the term potential energy out of context, you guys know that there's gravitational potential energy and there's spring potential energy, right? If there's a spring involved in like changing heights all at the same time, they might be referring to both of these collectively. If they just say potential energy, they might be referring to both of these. Okay, right, just a little thing to watch for. I've seen that in the past. And so, guys, what's the formula for energy in a spring? Is it F equals kx or is it E equals 1/2 kx squared? 1/2 kx squared, exactly. Right. Guys, I've been teaching this class many years. Students mix up those two formulas all the time, but you guys aren't going to because you know to look for it. Right. We're talking about energy, so that's 1/2 kx squared. Oh, by the time it gets to point B, well, it had to have made it around this loop. So let's see. I bet it's some height difference, but it better also be in motion. Both of those things better be true. Notice there's no friction, right? There's no friction on the track. Closed system. Okay. So what's one form of energy? Yeah, kinetic. I got some 1/2 mv squared at point B going on. What else do I have? Potential energy, mgh, that it took to get up there in the first place. Right, so that plus that. All right, it's got both of those. Maybe it started off with 100 joules of energy in the spring, and maybe it took like 10 joules to lift at that height, and the other 90 joules are now in its motion. Possibly, I don't know. Could be. Right. Right. So solve for the speed at point B. So I got 1/2 kx squared. So this is sum of energy initial or at point A equals sum of energy at point B. So 1/2 kx squared equals, well, it took some mgh to lift to that height. And then I have left over some 1/2 mv squared at point B. Forgot that. Okay. Guys, is mass going to cancel out on this one? Yes or no? No, because this 1/2 kx squared definitely does not have anything to do with mass in it. Yeah, guys, the mass will not cancel. In fact, if I take different masses, if I push this against the spring, and I push this against the spring, are they definitely going to have different speeds at the top? Yeah. So okay, so mass definitely does not cancel out. Okay. All right. So what we got here? I'm gonna subtract this over. So let's do 1/2 kx squared. Let's subtract off the mgh, and whatever's left over, you get the 1/2 mv squared. Okay. Like my example numbers were, what if this was 100 joules and it took 10 joules to lift it? So 100 minus 10, you have 90 joules left over to go into its motion. Okay. Times 2 divided by m square root. So times 2, it looks like kx squared minus 2 mgh. Divide down the m. That's divide by m, divide by m. And that gives you v squared. And then one last step is to take the square root. So I'll bring that over here. The speed of point B is, it's a big old square root. Okay, I got a kx squared on m, and then minus 2gh. Look at there. All right, that's all right, right? You guys good? All making sense. All right, next one. Ooh, bungee jumper. Bungee jumper. I think I'm gonna turn this one into a poster too. This is pretty good. Dives off a platform and barely touches the ground before the cord retracts, right? So guys, that springy bungee cord, you could basically treat it as a what? Spring. Yeah, that's what I'm looking for. Spring, right? We'll call it a spring, okay? And I bet that bungee cord has some unstretched length. But then when you start to stretch it, we'll consider that x as in F equals kx, or energy is 1/2 kx squared. So what have I got in the system? Guys, I'm thinking 3 objects in the system. What's one object? The bungee jumper. I heard the cord and the earth. There you go. Yeah, there's 1, 2, 3. There's all 3 objects you need. Right? The jumper has some mass. The cord has effectively a spring constant, and the earth is pulling with a force. Yeah, you need all those objects for the closed system. Guys, what type of energy at point A? Yeah, mgh, gravitational potential energy. Right. You know what? There's different ways to interpret this. Do you guys see the word dives off? Dives off, right? If you interpret that as he does like a running jump, then he would also have what kind of energy at the top? Yeah, plus 1/2 mv squared, right? All right, so kind of your interpretation. If you think he just kind of steps off, then all you have is just mgh. If he does a running jump, you also include the 1/2 mv squared. Yeah.
So if you do a running jump, it's still a closed system.
Yeah. Because we're considering like right after he's left the surface, right? Yeah, true. Because like I guess while he's running, there's a force that allows him to speed up running, right? But we're not considering that. We're considering like right as he's left the platform. Yeah. So point A is right after he's left the platform. Right. Because by the time he gets to point B, does he have any gravitational potential energy? No, because he has no height. Like he reaches down, maybe just goes boop and just touches the sidewalk. He has no height, basically. Does he have any speed here? At point B?
Oh no.
No. So he has no kinetic either. He has no gravitational potential. He has no kinetic. Where'd all the energy go? Into the cord, into the spring. So what's the form for that? 1/2 kx squared. That's right. Right. Hey guys, what's the speed at point B? 0 meters per second. Oh yeah. Boom. All right. You can set up this equation, but still 0 speed at the end. Right. Now, that's going from that point A to that point B. Do you guys think if you kept the process going, this cord would retract like boing and like bring it back up? Yeah. Okay. So there's more to the story, but we're just focused on snapshot point A and point B. Okay. All right. I got a couple of Atwoods lined up. I got this modified Atwood and I got this classic Atwood. But both of them have no friction, no rotational inertia about the pulley. Don't know about that. Right. So let's start with this modified right here. Guys, what's do I have to consider each of these masses M1 and M2? Yeah, they definitely each have inertia. In fact, M2 has a weight that matters also. What else do I have to also include? The Earth. Yeah, there you go. Right. You don't necessarily have to specify the string, although there's tension in the string. That's just internal to the system. I'm not even going to write that. So definitely the M1, M2 Earth system. Right. No, guys, here's a little more nuanced take two. Guys, what about this table? Do you have to include the table? Guys, isn't there a normal force from the table holding it up? Yeah. No, that's canceled out by the weight of M1 acting down. It's a wash. Right. Also, that normal force doesn't actually do any work on the block because the motion of the block is perpendicular to that force. So for all those reasons, you don't actually have to include the tabletop either. Right? But you have to include these 3 objects. AP could ask this multiple choice. That's the answer. So, guys, what type of energy at point A? Potential energy. So MGH. But guys, which block? Block 1 or block 2? Block 2. Guys, only block 2 is falling down. So only that has the gravitational potential energy. let's say at point B is like 1 millimeter above the floor. So it could be in motion, but it basically has no height. So what type of energy at point B? Yeah, we got some 1/2 mv squared for a block. Well, I guess each of the blocks, right? Block 1 plus 1/2 mv squared for block 2. Isn't that true? If you want to, you could even do 1/2 and then the collective mass of like m1 plus m2 and then v squared. Okay, because guys, is this v and this v? Are those the same v? Yeah, it's the same speed. Right? Now one's going down, one's going to the side, but I said earlier in class today, energy is like a scalar quantity. So a lot of times this v, I don't even call velocity for the next couple of weeks. I just call it speed. Okay. Okay. And you can solve for the speed if you wanted to, right? Okay. Well, since we're running low on time, here's the last thing I'll show you guys is I have posters for each of these. Here's the modified Atwood. Well, I guess it was a little more complicated, but we did a short version of that. And here's the one we're about to do. Okay, so the classic Atwood, right? So in the near future, we do have to finish this table, and I need to get some labs to you guys. So look for that next few days. All right, you guys have a good day.